So, Assalamualaikum brothers and sisters. This video is going to present chapter 5, Basic Bipolar Junction Transistor Amplifiers, at which we are going to do AC analysis for your BJT. Okay? BJT has always been used as linear amplifier, and in my previous lecture, I have informed that BJT must be biased in the forward active region. Okay? In addition, if the time varying output voltage is directly proportional to the time varying input voltage, then the BJT configuration circuit is referred to as a linear amplifier. What this statement means that if you give a sine wave, the output is also a sine wave. The amplifier did not alter the shape of the input signal. It's just amplifying it. That's why we refer to as the linear amplifier. Okay? So, because we are dealing with linear amplifier, so it applies superposition principle, which means that total responses is sum of responses of the circuit for each input signals alone, which means that firstly you perform this analysis, but you need to turn off your AC source. Next, you perform AC analysis and then you turn off your DC source. So for example, you can see this circuit here. It is a combination of AC and DC, kan? So these parameters, the voltages and currents, are sum of both AC and DC components, right? So what it means is that, for example, your base current, it is equivalent to the DC and the AC component, and so on. Okay, but in order to get these components, for the DC base current, you're going to do your DC analysis, and then for your AC base current, you're going to do your AC analysis, right? You can see here, for DC analysis, we turn off the AC supply, and then you do your analysis to get the DC component, and for AC analysis, you turn off the DC power supply and we get the components for your AC analysis. The thing is, for AC analysis, it's not just a simple KVL, BE loop, CE loop. It is a bit more challenging. So that's why we have a separate chapter for your AC analysis. So do you still remember when we did our AC analysis for diode? So what we did was, in the video you can see that you need to do both analysis as well. So for DC equivalent, okay, you're going to represent your diode as a battery, for example, if you are dealing with model 2. Then you do your analysis to get the diode current, right? After that, you turn off your DC supply and represent your diode as a resistor, RD. And this resistor is equivalent to the thermal voltage over the DC diode current. So what about BJT? So for BJT, this NPN transistor will be represented as this equivalent circuit or this. But in this video, I'm going to cover this equivalent circuit only. The only difference between these two is the term GMVBE, and this circuit is using beta IB for the current source. So the small signal parameters, which is also the AC signal parameters, are R-pi, GM, and R0. To calculate R-pi, GM, R0, you can see here, you need all the DC components for collector current. So therefore, similar to your diode, you need to do your DC analysis to calculate the DC collector current. Then only you can compute what is R-pi, GM, and R0. So this R0, if you remember, is the resistance when we are dealing with the IC versus VCE graph. And then when the slope is extrapolate, you see the early voltage. So this is the R0 that I am referring to. So you can see here, if your early voltage is infinity, you will get R0 equivalent to infinity as well, which means that it will be open circuit. So this example is very straightforward. You are given all the parameters and you are asked to calculate what is IC and then compute what is R-pi and R0. So again, this is just an example where you're going to use the small signal parameters here. So you can try out and the answers are given to you. Okay, so when we talk about amplifier, it means that you're going to amplify the input signal to become bigger. So we are dealing with gain, right? So if you give a voltage signal, then it's voltage gain. So if you give current signal, then it will be current gain, right? So we are going to cover voltage gain and current gain. For this chapter, there are 3 configurations of BJT amplifiers: common emitter, common collector, and common base. So let's have a look at the first configuration, which is the common emitter amplifier. Okay, so for common emitter amplifier, the output is measured at the collector terminal and the gain is a negative value. So for common emitter, there are 3 types as well: emitter grounded, emitter connected with RE, and emitter connected with bypass capacitor. So in this video, I'm going to explain about the common emitter where the emitter is grounded. So I'm not sure whether you still remember this configuration, which is from chapter 1. Okay, this is voltage amplifier, right? So you have the input resistance, output resistance, this is the open circuit voltage gain, and this is the input signal, and this is the output signal. Okay, so these are the steps for you to calculate the components for this voltage amplifier. So let's do one example. Okay, so this time we are not going to ignore this portion, okay, because this is the AC signal, right? This is the voltage divider biasing configuration, which you just learned in chapter 4, alright? However, during this analysis, your coupling capacitor ni will be open circuit, okay? Because capacitor, the property is coupling capacitor, okay, open circuit during DC and short circuit during AC. Okay, so because of this property, when you are doing your DC analysis, you are not going to connect with this VSRS because your coupling capacitor will be open circuit. So you are only going to deal with this area, and you're just going to do the steps for your Thevenin equivalent, which is shown here in this slide. So this is your BE loop. You can see this is your RTH and this is your VTH. Basically in this slide, I'm just showing the BE loop because we just need to calculate what is IC so that you can calculate what is RPi, R0 and GM. The question gives the value of VA. Okay, you can see in this slide, the value of VA is 100 volt. So that is why there is a value for your R0. Okay. So now you have done your DC analysis where you have converted this circuit into your Thevenin equivalent, VTH, RTH, and just now you did the BE loop to calculate the collector current, and you have computed RPi, GM, and R0. Okay. So now in order to do your AC analysis, you have to turn off all the DC supplies, which are VTH and VCC. So you can see here, when it is turned off, it will become short circuit. So I'm going to show you how to convert this circuit, okay, into the AC equivalent using the whiteboard. Okay, so this is a circuit in your slide where your VCC and VTH are already turned off. Now I am going to label the terminals. So collector, emitter, and this is your base. So now I'm going to transform this into the AC equivalent. Alright. So firstly, you're going to start with the base, collector, emitter, like this, right? So between base and emitter is your RPi, and then between collector and emitter is your current source, and then you have R0. Okay, and don't forget that the output for common emitter is measured at collector, right? So this is V out. Okay, so this is your AC equivalent for NPN BJT. So now we're going to connect this with the other resistors in the circuit. Alright, so let's start with emitter. So now emitter is directly connected to ground. So normally ground is always at the bottom. So emitter just straight connect to the ground. Now collector is connected with RC. Okay, and your RC is directly connected to ground because this is your VCC off. So since that is the case, you just straight away connect RC to ground like this. Okay, and this is what? This is your VCC off. Alright, next is your base. Although your RTH is horizontal, but because it is directly connected to ground, you can directly make it vertical like this, just like your RC. And this is what? This is your VTH off. Okay, so your DC supplies are off, yeah, during AC analysis. So this current source is GM VBE. So VBE is here between base and emitter. So this is your VBE. Alright, so that's it. That's how you transform this circuit into the AC equivalent. I'm going to do the 5 steps to get the open circuit voltage gain. Alright, so I'm going to wipe this part off. I'm going to transform this circuit into a more simplified looking circuit because your emitter is directly connected to ground. So I can drag this red portion of your circuit to ground as well, so that it is easy for you to do your analysis, right? So let's start with RTH. Okay, so all these are ground. Okay, then is your RC over here. Your RPi, okay, connected to E, but then E is also to ground, so I can drag my RPi like this. Okay, and similarly GM-VBE, C to E, directly to ground, so I can do that as well, just directly to ground. Similarly your R0. Okay, and this is my R0. This is GM-VBE, and this is my V out. Okay, collector terminal, base, and this is my emitter. Okay, so now we can do the 5 steps to calculate the open circuit voltage gain. Right, so this is my output side and this is my input side. Okay, so the first step is the calculation of the output resistance R0. So if you look at the output side, these two are in parallel. So R0 is equivalent to the small R0 parallel with RC. Okay, which is equivalent to R0, RC, R0 plus RC. Next, step number 2 is to find what is the equation of V out. Alright, so because you have simplified this part, your output side will become like this. So this is my R0 and this is my GM-VBE, right? Okay, and this is your collector terminal and this is my V out. Okay, so the current that flows through your R0 is this current. Okay, so it will keep on going through this loop. Therefore, your V out can be calculated using Ohm's law. So V out equivalent to GM-VBE R0. Okay, however, because the current goes this way, the polarity of your V out should be like this. However, the question puts the convention of V out to be plus at the top and minus at the bottom, and because of that, that is why you have the negative sign. Okay, and that's where the negative gain for common emitter comes from this V out being a negative value. Okay, so that's the first 2 steps for the output side. So I'm going to wipe this off because I need to maintain this circuit for your reference. Right, so step number 3 is the calculation of the input resistance. So now we shift to the input side. So what can you see? You can see that RTH is in parallel with RPi. So Ri is equivalent to RTH multiplied with RPi, RTH plus RPi. So that's the equivalent resistance for Ri. Okay, next is the representation of VBE with Vi. Okay, so this is your VBE. Alright, your voltage amplifier from chapter 1 is like this. Okay, so this is your Ri, this is AVOC VI, and this is my R0, right? So this is your V out and this is your VI. Okay, so this amplifier is simplified from this actually, and therefore what I want to highlight here is this VI here is actually the measurement of voltage from base to ground. Okay, so if I want to compare this with this is where my VI is. VI, alright, from base to ground. So with that in mind, that is why step number 4, if I want to represent VI as VBE, you can see that actually these two are in parallel. So that's why VI is equivalent to VBE. Alright, step number 5 is finding your AVOC. Okay, so I think I can remove this part now. So step number 5 is for you to derive what is AVOC. Okay, so you have calculated all these parameters. You have calculated what is Ri, okay, and your R0. So now you need to find what is AVOC. Okay, so this is my V out and this is my V in. Okay, so because there is no load, AVOC VI is equivalent to V out. So this is from your chapter 1. Okay, so your V out is equivalent to minus GM VBE R0, right? This is from step number 2. Then your AVOC, your V in here is equivalent to VBE, which is from step number 4. So you can cancel out VBE here, and you are left with AVOC equivalent to minus GM R0, which is minus GM R0 parallel with RC, which is from your step number 1. Okay, so that's the derivation of AVOC. So now we are going to connect this amplifier, okay, with the input signal Vs. And after that, you need to derive what is the voltage gain V out over Vs. So I'm going to remove this part now. So your voltage amplifier is like this, okay. So now you can connect the RS and Vs. So this is your RS and this is your Vs. Okay. So now you are going to just simply do the procedure from your chapter 1. So there is no load, right? So AVOC VI is equivalent to V out because there is no load. Okay. So this is what you have obtained here. Okay. So minus GM R0. Okay, this is your VI equivalent to V out. However, your VI now is different because the input signal connected to your amplifier now. So you need to use voltage divider, right? So VI is equivalent to RI plus RS multiply with Vs. Okay, so I'm going to remove this part. So now minus GM R0 RI plus RS Vs equivalent to V out. Therefore, V out over Vs is equivalent to, you just bring Vs over, minus GM R0 RI plus RS. So that's it. That's how you can derive the voltage gain V out over the input signal Vs. So the first 5 steps is actually for you to calculate what is AVOC, and then you can use AVOC for this configuration to finally derive what is V out over Vs. Okay, let's go back to the slide. So now let's go back to the example in the slide. Okay, so we're going to solve this. So these are the 5 steps. And so step 6 and 7 is actually when you have already established the voltage amplifier and connect the input signal as I have shown on the whiteboard. Okay, so as I mentioned just now, this is the portion, this box here, that you're going to convert into the voltage amplifier. So you have calculated these values. Alright, so the first step is the R0, hence R0 parallel with RC is 5.677 kilo ohm. And then equation of V out, where V out equivalent to minus 207.21 VBE. Okay, and then R in is RTH parallel with R pi, and we got this value, and VI equivalent to VBE. Okay, so step number 5 is to compute the open circuit voltage gain, right? So this is the voltage amplifier, and now you would like to calculate what is AVOC, kan? So because there is no load, AVVI equivalent to V out, and because VBE and VI is the same value, they can cancel out, and this is your open circuit voltage gain, right? After that, you can see here, we connect with the input signal, right? And we use voltage divider to compute what is the new V in, and because there is no load, V out again equivalent to AVVI, right? So this is the open circuit voltage gain multiply with the V in, and you can see the new gain is lower because of the effect of RS, right? So the question in your assessment is normally asking about this voltage gain, alright? Not the open circuit voltage gain. So I hope that you can take note on that. So in this example, your emitter is grounded. So basically it's the same steps. However, this time, not only you're going to connect the input signal, you are also going to connect the load resistor at the output side of your amplifier. So the steps are almost the same with the previous example, the DC analysis, and then you follow the steps to calculate what is the AVOC. So the AVOC here is minus 12.831. Okay, and then this is the part that is interesting that I would like to highlight to you. Okay, so not only there is a connection with the input signal, but this time you need to connect with the load resistor here. So the voltage divider is at the input side and the output side here. Okay, because now V out is measured across RL, where V out equivalent to RL over RL plus R0. Okay, in the previous example, because there is no load, V out is straight away equivalent to AVVI kan. But this time you need to use voltage divider. So the voltage gain is minus 10. Okay, so that's it. That is the first part of your common emitter, which is the common emitter grounded. So in the next video, I will proceed with the common emitter with emitter resistor. Okay, so I'll see you then. Assalamualaikum. Bye.